We are now going to look at the unit circle, something many of you seem to be dreading. Hopefully this won't be as bad as you think it is. So I started by just drawing a circle on a coordinate plane. And the unit circle is called the unit circle because it has a radius of 1 unit. So you already know this, actually. This isn't surprising, x and y axis. If I go over 1 unit in the x direction, I'm at the coordinates 1, 0. If I go up, 0, 1, etc. So that's nothing new. What we're going to be adding is a few extra angles in there that have some nice properties, and they can be derived if you take a look at any triangles where you have one vertex here at the origin, 0, 0, and one on the unit circle. And what you're trying to make is right triangles going around using these 2 points and then one on the x or y axis here, and figuring out based on a hypotenuse of 1 what the lengths of the sides are. And because of what you know about SOHCAHTOA, cosine is going to be the x value because it's adjacent to this angle we're looking at. We're looking at this one when we do it, the one about the origin. They don't always match, of course. This is just an isosceles triangle. And so x is the cosine and y is the sine, or the height, because it's opposite over hypotenuse. Now, this may look scarier. I'm going to do this in first labeling the degrees and the radians and then talking about what these values are going to be. And it is absolutely fine. So weirdly, we do start here when we're talking about angles on the unit circle and go counterclockwise. This is then 0 degrees. And we're going to look at angles made by 30s and 45s. So I'm going to first just count by the 30s. This is then 30 degrees. Here's 30 more degrees, which makes 60. 30 more makes 90. Going around all over here, we have 120 degrees. Here we have, I guess this was supposed to be my degrees, it doesn't matter. 120, 150 degrees. I'm skipping the 45s. I'm going to come back, 180. 210, 240, 270. So I'm guessing that this is also not too scary for you as you count by 30s going around. We've done a full circle and we're back. That's important here too, because you can go on forever and ever, and also in the other direction, going this way. This would be, for example, negative 30 degrees, going backwards or clockwise. We can also count by 45 degrees. So 0, 45 is splitting these quadrants in half. 45 is 90, another 45 is 135, 180, 225, okay, 270, and then we have 315 degrees. So these are the angles that we're going to be able to use the unit circle with. We can't just use it with any angle. Now, in order to see the pattern, what you're going to need to remember is this: 0, 1, 2, 3, 4. Okay, I'm simplifying it a little bit, but it's quite nice. So we're going to have 0, should have given myself a little bit more space, is equal to 0 over 2, right? That's equal to 1 over 2. We're going to have square root. I'm going to explain my change here in a second. I actually wanted to include the square roots here. 0, 1, square root of 2 over 2, square root of 3 over 2, and square root of 4 over 2. Okay, so these are the numbers you have to remember. You can see them forming in a pattern: square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3, that's a 3, over 2, and square root of 4 over 2. And some of these can be simplified. Whoa, about to lose this. Some of these can be simplified. And that's what's going to be the number you see, and it may not then look like the pattern that's so comfortable. Okay. I should make that clear. These are not equal. These are the numbers you're remembering. What these actually do equal is square root of 0 is 0. Anything, 0 divided by anything is 0. Square root of 1 is 1, and 1 divided by 2 is a half. Square root of 2 over 2 is fully simplified. So is square root of 3 over 2. Square root of 4 is 2, and 2 over 2 is 1. These are the numbers that you see when you look at the unit circle. And they don't really look as much like a pattern as these numbers. So by just remembering you're working on 0, 1, 2, 3, 4, 3, 2, 1, 0, 1, 2, 3, 4, you're going to be fine. So now we're just going to go around and label all of these, thinking about the length along the x-axis of each of these triangles. So like here's one triangle, or here, or maybe you say here's another triangle, okay, and the height of them. So if you start this point, we already said you know this. This is, I go over 1 and up 0. Okay, I'm going to start at the 0. It doesn't matter. 0, 1, 2, 3, 4. And remember the 4 is 1. This is the same height you've already seen. And then you're just going to count back down. 4, 3, 2, 1, 0, 1, 2, 3, 4, 3, 2, 1. Okay. So not so bad. Of course, the signs are going to change in some of the places. I'm going to come to that in just a second. We're going to do the same. 4, 3, 2, 1, 0, 1, 2, whoops, here we go, 3, 4, 3, 2, 1, 0, 1, 2, 3, 4. And then we have some signs we're going to put in, but I do want you to see these are always a pair, square root of 3 over 2.5. Sometimes you'll see them one first, the other one second, or the other way around. Remember that the shorter one, these are always going to be for the 30, 60, 90 triangles. The shorter side, like if you take this, is going to be opposite this, the shorter side is going to be opposite the smaller angle. Ooh. Not really thinking there, because this is the 60. It's not this, just to be clear. That's why I was confused for a second. This would be the 60 degrees. I'm just labeling that line, this point here, is subtended by this 60 degree. And the 45s are always going to be the same, because those make isosceles triangles, just reflected about this circle in the coordinate plane. So square root of 2 over 2 always goes with square root of 2 over 2, regardless of where you are. And 1s and 0s always go together. They can switch. Now, thinking of the signs, in this first quadrant, they're both positive. In the second quadrant, we have negative x's. So that's negative. In the third quadrant, they're both negative. Maybe that's a little difficult to see. And in the fourth quadrant here, we have, remember that the y's are negative. So that's also nothing new, this particular thing. We're just finding patterns that we're working on to create this unit circle. As you do this, again, that same idea of cosine, sine. Cosine is always the x value and sine is the y value. So if you wanted to say, well, what is the sine of 120 degrees? Here's 120 degrees, and sine is the y value. It's the height. It's opposite this 120 degrees. So sine is equal to square root of 3 over 2. You'll see that there are a couple places, actually, where that's true. It's also sine, there are a few different angles that have the sine value of square root of 3 over 2. You could also say, well, what angles, maybe, given a domain, have a cosine of negative square root of 2 over 2. Cosine is the x values. So here's an x value at 225 would be one possibility. Or this also has a negative negative square root of 2 over 2 at 135 degrees. There's an infinite number of solutions. Let's just pretend this is from 0 to 360 degrees. For the sake of time, I'm not going to label the radians. You can look at the other one, but we can also, maybe I will. I lied. We'll just go through it because we're counting for the 30 degrees by pi over 6. So here's 1 pi over 6. Here's 2 pi over 6, or 1/3 pi. This is 3 pi over 6, which can be reduced. 4 pi over 6. 5 pi over 6. 6 pi over 6. This is 7 pi over 6. 8 pi over 6. 9 pi over 6. 10 pi over 6, which we'll say 5 pi over 3. And 11 pi over 6. 11 pi over 6. 12 pi over 6. There's also 0 pi's. And then you have the same thing with, here's 1 pi over 4. If you're really confused about these, you do need to go back to the last one. 2 pi over 4. Here's 3 pi over 4. 4 pi over 4. 5 pi over 4. 6 pi over 4. 7 pi over 4. There we go. And 8 pi over 4. And there's your complete unit circle. And here it is all drawn for you. We can also use these ideas to work through some of this. This is always true because of the unit circle. Sine squared cosine squared equals 1, the Pythagorean identity. Because when you think of these on the unit circle with a radius of 1, wherever you are, you have a right triangle with a hypotenuse of 1. So if sine is the height and cosine is the length, you get this Pythagorean identity, which is really nice, regardless of whether you have a theta on the unit circle or not. You can always use this. It has many, many useful properties to it. Tangent is also the idea of the slope. It is sine over cosine. You may be aware of that. You can also work through it by understanding the opposite over hypotenuse. Divided by the adjacent over hypotenuse gives you opposite over adjacent, which is the tangent. And it ends up just dividing these, and you can kind of think of it, you'll see it come back up in calculus. Tangent is like the slope of a line. So if you have this line right here, well, opposite over adjacent gives you 1, and this line has a slope of 1. Okay, you can see negative slopes with the same idea. Here's a less steep slope because you're dividing, but negative, so you have negative 1/2 divided by square root of 3 over 2, and you'll get negative 1 over the square root of 3, or negative square root of 3 over 3. So you can work through that here. And these identities just let you find similar angles here on the unit circle to find more of them given in radians, but you could do it with 180 degrees in degrees as well. So if you have like sine of 30, I'll use radians, of course, of pi over 6 is 1/2. Well, if you do a pi minus pi over 6, you get here and you get the same 1/2. That's what that's saying. In cosine, that will be a negative value because you're swapping where it is in the quadrants according to being to the right of the x-axis, or the y-axis, or the left. So you get the negative value of cosine. You'll see those are swapped. And tangent, you have the same idea of the slope of the line, or you can say, well, if I divide sine and cosine, you're going to get the negative equivalent. Those are useful. These are in your formula booklets. You'll be probably quite comfortable with them regardless. So let's use these and maybe my unit circle here as needed to think through what these could be. If you know sine and cosine, you know that tangent is sine over cosine. So negative square root of 2 over 2 divided by square root of 2 over 2. Well, that's going to be negative 1. And where does the angle have this property? Well, where is the sine negative? So underneath the x-axis, and the cosine positive over in quadrant 4. Square root of 2 over 2, negative square root of 2 over 2. I'm going to do this in radians. This is now just to get more common. We could say also 315 degrees, or 7 pi over 4. Or any number of solutions, just depending on where we are in our domain. So now we're going to look at this one. Where is theta negative 3 pi over 2? Remember, the negative angles go clockwise then. Here is negative 1 pi over 2, negative 2 pi over 2, negative 3 pi over 2. That's the same thing as positive pi over 2, for example. So we have a cosine value of 0. We have a sine value of 1, for the y. Tangent is sine over cosine. It's undefined because we can't divide by 0. And this last one, where does sine have a value of 1/2 and tangent have a value of negative square root of 3 over 3? Well, remember, tangent of theta is sine of theta over cosine of theta. Okay, you could also think through this, and we can look at that as well. So negative square root of 3 over 3 equals 1/2 divided by something. If you swap those, we get that cosine of theta equals 1/2 divided by this tangent of theta. Dividing fractions is multiplying by their reciprocal. And we get negative 3 over 2 square roots of 3 make the radical go away in the denominator by multiplying by the special 1, and you get negative 3 square roots of 3 over 2 times, now no square root, and those cancel. So we get negative square root of 3 over 2. So where does this happen? We want to find where the sine is a half, the cosine is negative square root of 3 over 2. Sine is a half, cosine is negative square root of 3 over 2 right here. So at 5 pi over 6, or any multiple of those. You can also see we could have figured that out graphically by understanding here where is sine a half, here and here, and I want the negative slope, tangent, here. And then we could have also found the cosine there. Okay. Now we have a slightly different domain given to us here. Given that sine of theta is 2/3, this is not 1 on the unit circle. Let's see what we can do without that. And this domain for theta, find cosine of theta and tangent of theta without finding theta. But I do know that sine squared of theta plus cosine squared of theta is equal to 1. Another way you can write this is sometimes weird to understand that that's squaring the whole thing. It's not squaring the angle. That might be easier to understand now. Well, sine of theta is 2/3. You shouldn't usually write it like this, but it's okay if you do. So we get that cosine of theta equals 1 minus, and the squared is 4 over 9. Okay. And then if you, that's still there, of course. And if you take the square root of this, equals the square root, when we take the square root plus or minus, 5 over 9, so plus or minus the square root of 5 over 3. Because we can't take the square root of 5, but we can have 9. Now, it does say because we're in this second quadrant, when theta is between 90 and 180, which does also say we should work in degrees, cosine is going to be negative there. But given that we want theta between 90 and 180, that means cosine of theta is equal to the negative value. If we'd have a different domain, then maybe we could include those. Okay. And then tangent of theta is going to be sine of theta over cosine of theta. So 2/3 over negative 5, the square root of 5 over 3. Dividing fractions is multiplying by the reciprocal. So negative 2. Don't leave the radical in the denominator, but multiply by the special 1. And there you have tangent. Okay. Another example, find all thetas in this domain. So now working in radians, we actually are going around the circle twice, such that the sine of theta equals a half. If I look here, sine of theta equals a half. Here, not down here, but if I'm going all the way backwards, I get it at this spot right here. But if I'm going backwards, I actually go back negative 7 pi over 6. Because this is 1 full pi over 6, another pi over 6, 7 pi over 6, and almost the full amount. I'm also going back negative 11 pi over 6. I'm just writing this in order. Okay, so I went back, starting all the way back here. I've got my first one, there's the second. Now I'm at 0, and I can go around again in the correct positive direction. Excuse me, that's just pi over 6 first, and I'll get to the 5 pi over 6 now. So those are all of the solutions given this domain of actually going around the circle twice, okay, where sine of theta equals 1/2. And finally, the associated acute angles are just saying find that in the first quadrant where both cosine and sine are positive. The associated acute angle always helps to just think of this. Where is this on the unit circle? Negative 200 degrees is, I'm now going in the clockwise direction, 200 degrees, which puts me about, where is 200 degrees? Sorry. Right here, there's 180. So 200 is about 20 more here. So this would be 200 degrees. Okay. And the associated acute angle is you have this 30-degree triangle. Okay, so 30 degrees. Okay. 9 pi over 2. If you go forward and you just keep going around the circle here, 9 pi over 2 is going to be, there's 8 pi over, excuse me, there's 4 pi over 2, 8 pi over 2, 9 pi over 2 is just, oops, excuse me. I need to make sure I'm counting by the right amount. A little bit of a mishap there. Let me go back here. I know this is going on longer than intended. Okay, 9 pi over 2. Excuse me. There's 1 pi over 2, 2, 3, 4, 5, 6, 7, 8. 9 pi over 2 is the same as pi over 2. Okay, there is no really associated acute angle for this. And 2 pi over 3, if I were to reflect that, here's 2 pi over 3. That's the same as an acute angle of pi over 3, just to be able to think of like what is the shape of triangle I'm trying to make in the first quadrant. And that's a way to think of that.